A world like ours, under a red sun? If you woke up tomorrow under a dim red sky on a planet almost the size of Earth, would it still feel like home or like an alien trap? We talk a lot about finding a second Earth, a safe backup, a place where humanity could not only survive, but live, work, and raise families. But while the phrase Earth-like sounds comforting, it hides a difficult question. What would everyday life actually feel like on a world that only looks familiar on paper? In the hunt for alien life, we have focused on planets that match Earth in size and in starlight. We know that our own planet sits in the Goldilocks zone of the Sun, where liquid water can exist on the surface. This means that when we find another world with similar energy from its star, our hopes immediately rise. Could this be a place where oceans, clouds, and maybe even forests might one day appear? At least, that was an abstract idea until astronomers took a second look at some old Kepler data. Hidden in the noise was a small, dark world passing in front of a faint red dwarf star about 300 light-years away in the constellation Cygnus. They called it Kepler 1649c. And it should be noted that this planet is one of the closest matches to Earth we have ever seen in terms of size and the amount of starlight it receives. Kepler 1649c is only slightly larger than Earth. It completes an orbit in just 19.5 days, so its year would pass in less than 3 of our weeks. Yet, despite that short orbit, the energy bathing its surface is around 3/4 of what Earth gets from the Sun. On paper, that places it right in the conservative habitable zone of its tiny star. An Earth-like world under a very un-Earth-like sun. Because this sun is not a yellow star like ours, it is a small, cool red dwarf. Its light would stain the sky in deep oranges and crimson. Shadows would look darker. Plants, if they ever evolved here, might even be black or dark purple, optimized to drink in every precious photon. Optimistically speaking, it sounds almost idyllic. But while the energy looks gentle, the reality may be far more hostile. Red dwarf stars can be volatile, blasting their planets with powerful flares and radiation. This means the same star that places Kepler 1649c in the habitable zone might also be violent enough to slowly peel away its atmosphere, evaporate oceans, and sterilize its surface. Is this a cradle for life or a beautifully lit trap? So let's begin. So it's time to find out the truth about what life on this world might actually feel like. By the end of this journey, we will picture the sky, the weather, possible oceans, and even speculative ecosystems on Kepler 1649c. And then we will have to ask ourselves, if we had the chance, would we dare call it home? Why this one planet could rewrite our idea of home. And that question, would we dare call it home, is exactly why this one planet matters so much. Because out of the billions of stars in our galaxy and the thousands of exoplanets we have already found, only a tiny handful look even remotely Earth-like in 2 crucial ways: their size and the amount of energy they receive from their star. Most worlds we detect are either searing hot giants pressed up against their stars or frozen, distant rocks. In the hunt for alien life, those are interesting, but they are not prime real estate. What we really want are planets with solid surfaces, roughly Earth-sized, sitting in that narrow Goldilocks zone where liquid water could exist. This means the planet cannot be too big or too small, and it cannot be baked or starved by its star. Kepler 1649c quietly checks both of those boxes. It is almost the same size as Earth, only about 6% larger in radius, and it orbits an M-type red dwarf in just 19.5 days. Yet, because its star is dimmer than our Sun, it receives only about 3/4 of the light Earth gets. On paper, that places it right inside the conservative habitable zone, a region where an Earth-like atmosphere could, in principle, keep surface water liquid. But while the numbers look comforting, the reality is far less certain. We cannot see its surface directly. We do not yet have a confirmed atmosphere. We do not know if there are oceans, continents, or only bare rock. Its red dwarf star may bathe it in flares and high-energy radiation that strip away air and water, sterilizing the surface. Or, paradoxically, that same violent history could have sculpted a dense, complex atmosphere, creating strange, but still habitable climates, perhaps with a permanent twilight band between scorching day and frozen night. It should be noted that this is not just an academic puzzle. Red dwarfs are the most common stars in the Milky Way. If life is widespread, many living worlds may orbit these small, cool stars. Our long-term survival as a species may depend on knowing which of these red dwarf Earths are truly habitable, and which are only statistical mirages. If we ever build starships, we will not be able to visit every candidate. We will have to choose. So it's time to find out the truth about how fragile our picture of this planet really is. Because, astonishingly, Kepler 1649c was almost lost entirely, buried in the noise of faulty data processing and dismissed as a false signal. Optimistically speaking, we caught it just in time. But what else did we miss about this world, hiding in that same noise? And what happens when we look closer? Meet Kepler 1649c, the almost lost twin. To answer that, we first need to meet the world that almost slipped through our fingers. What kind of planet hides in the noise, only to reappear as one of the most Earth-like worlds we have ever found? So let's begin with its address in the universe. Kepler 1649c orbits a small, cool, M-type red dwarf about 300 light-years away in the constellation Cygnus. On a star map, it is just another faint point in a crowded field. But while the star looks unremarkable, the system it hosts is anything but. Buried in the original Kepler mission data, this planet was first flagged, then rejected, and only later recovered when astronomers went back through the observations by hand. The basic statistics are surprisingly familiar. Kepler 1649c is only about 1.06 times Earth's radius, essentially the same size as our own planet. That alone is rare. Most exoplanets we find are bloated gas giants, or bulky super-Earths, not compact Earth-class worlds. This means its surface gravity is likely similar to Earth's, and the planet is probably rocky rather than gaseous. It should be noted that we do not yet have a precise mass, but every piece of data we do have points toward a solid terrestrial planet. Its orbit, however, is very different. Kepler 1649c races around its red dwarf in just 19.5 Earth days. A year there is shorter than a typical vacation here. Because the star is much dimmer than the sun, the planet has to hug close to receive enough energy. Even so, it only gets about 75% of the sunlight Earth receives. This means it sits squarely in the star's conservative Goldilocks zone, where liquid water could exist on the surface if an atmosphere is present. In the hunt for alien life, that combination is gold. Similar size, similar insulation, a stable orbit right in the habitable zone of its star. When astronomers rank Earth-like exoplanets, Kepler 1649c consistently rises to the top because it checks all three boxes at once. It is not just Earth-sized or just temperate, it is both, around a star that will likely burn for trillions of years. But while the recipe sounds familiar, the kitchen is very different. Instead of a bright yellow sun, we have a dim red dwarf. Instead of a spacious orbit, we have a tight embrace. That contrast makes Kepler 1649c a prime test case for red dwarf habitability. If any such planet can maintain oceans, clouds, and a protective atmosphere under a red sky, this might be it. Optimistically speaking, that pushes Kepler's 1649c beyond pure science fiction. So it's time to find out the truth. Under these conditions, does an Earth-like world stay friendly to life, or turn strange and hostile in ways we are only beginning to imagine? From Kepler's ghost data to a second look. To answer that, we first have to ask something less glamorous, but just as important. How did we even know Kepler's 1649c was there in the first place? Because for years, as far as our computers were concerned, this planet did not exist. In the hunt for alien life, the Kepler mission was our first great census taker. Kepler was a space telescope that did something deceptively simple. It stared at more than 100,000 stars at once, measuring their brightness over and over for years. Whenever a planet passed in front of its star, the starlight dipped by a tiny fraction. One transit, 2, 3, in a repeating pattern, and suddenly you had a world, its orbit, even an estimate of its size. But while that sounds straightforward, the reality was a blizzard of noise. Stars flicker, spacecraft wobble, detectors age. So the Kepler team built automated pipelines, chains of algorithms that scanned the raw data for those tiny, periodic dips, and then tried to decide, is this a real planet or just a glitch? It should be noted that the vast majority of candidate signals were false alarms. The software had to be ruthless. Kepler 1649c fell on the wrong side of that digital verdict. Its signal was faint, its host red dwarf naturally variable, and the transits were buried among instrumental artifacts. The pipeline flagged it as a false positive and quietly filed it away. One of the most Earth-like exoplanets in the entire archive was, for all practical purposes, thrown into the trash folder. So what changed? Years after Kepler stopped collecting data, a new wave of astronomers and data scientists went back to the archive with fresh tools. They combined improved algorithms with careful human inspection, asking a simple but powerful question. What did we miss? This means they were not just looking for obvious planets, but for subtle, borderline cases the first software had rejected. Here is the pattern interrupt. Kepler's discoveries did not end when the telescope died. In some ways, they were only beginning. In 2020, this reanalysis effort noticed something odd in the light of a small red dwarf about 300 light-years away. A repeating 19.5-day dip that, when modeled, pointed to a planet just 1.06 times Earth's radius, receiving about 3/4 of the starlight we get from the Sun. Suddenly, Kepler's 1649c stepped out of the noise and into the spotlight. So it's time to find out the truth. This was not just another entry in a catalog. This was a near-miss Earth, a world in the Goldilocks zone that our own software had nearly erased. Optimistically speaking, that realization forces us to ask a deeper question. If we almost lost this planet, how many other potentially habitable, Earth-like worlds are still hiding in the data, waiting for us to look again? And once Kepler's 1649c was confirmed, the real verdict phase began. Under that dim red sun, could this planet actually support an atmosphere, oceans, and maybe even life? To answer that, we have to move from discovery to environment and step onto its surface in our imagination. Paradise or radiation-baked wasteland? So what kind of world are we really talking about here? Is Kepler's 1649c a gentle, cloud-draped ocean planet, or a radiation-baked, airless rock locked in eternal day and night? On paper, it looks almost disarmingly friendly. This planet is just a touch larger than Earth, about 1.06 times our radius. It sits in the conservative Goldilocks zone of its red dwarf star, completing an orbit in only 19.5 days, yet receiving roughly 75% of the light Earth gets from the sun. In the hunt for alien life, those are exactly the kind of numbers that make astronomers sit up straight. But while the basic metrics whisper habitable, the environment around it might be screaming something very different. To get that pleasant, Earth-like level of starlight, Kepler's 1649c has to huddle extremely close to its star, far closer than Mercury is to ours. This means it lives deep inside the star's magnetic and radiation environment, where intense ultraviolet and X-ray flares can slam into any atmosphere over billions of years. So which is it? A mild world wrapped in protective clouds and temperate seas? Or a stripped, lifeless rock, its sky filled not with blue, but with raw, unfiltered radiation from an angry red dwarf? It should be noted that we do not yet have a single direct image of its surface. We have no confirmed detection of an atmosphere, no clouds mapped, no oceans seen glinting in the starlight. All we have are the transit data from Kepler, estimates of its size and orbit, and computer models based on similar systems. This means every picture we paint of Kepler's 1649c right now is a carefully informed guess, not a photograph. Optimistically speaking, one family of models suggests that if the planet started with a thick atmosphere and enough water, tidal locking to its star might not be a death sentence at all. Instead, powerful winds and jet streams could carry heat from the blazing day side to the frozen night side, creating a permanent ring of twilight around the terminator where temperatures are almost Earth-like. You could imagine standing in that eternal sunset, oceans lapping at the shore, the red star hanging motionless in the sky. But another set of models, using the same kind of red dwarf activity we see elsewhere in the universe, leads to a very different ending. Flares strip away the upper atmosphere. X-rays erode lighter molecules. Over hundreds of millions of years, oceans evaporate and are lost to space. What remains is a tidally locked, bare rock, its dayside scorched, its nightside airless and silent. So it's time to find out the truth. By looking more closely at the star, the orbit, the physics of tidal locking, and potential climate patterns, we can start to weigh these two futures against each other. And here is the personal version of that question. If you had to decide right now, would you step off a lander onto Kepler's 1649c without a suit? Or would that be signing your own death sentence? Who's talking to you, and where we're going? So who is actually asking you to make that life or death call about Kepler's 1649c? I'm Host, and this is Channel, where we take the raw data from missions like Kepler and JWST and turn it into something you can almost feel under your feet. In the hunt for alien life, we do not just list numbers on a screen. We try to step onto the planet in our minds and see if it welcomes us or kills us. So let's begin by laying out exactly where we are heading in this episode, because this is not a random tour through space. First, we start with the star itself, Kepler 1649, a modest M-type red dwarf about 300 light-years away in Cygnus. How bright is it? How violent? How does its size and energy output shape the narrow Goldilocks zone, where a world like Kepler 1649 can orbit? Then we move inward to the orbit and the physics. Why does this planet whip around its star every 19.5 Earth days? What does that do to tides, to seasons, to the likelihood of tidal locking, with one side in eternal day and the other in endless night? This means we will talk about gravity, radiation, and orbital mechanics, but always in terms of what you would actually notice if you were standing there. After that, we build a climate and a sky. Using what we know about the planet's size, the starlight it receives, about 75% of what Earth gets from the sun, and what similar worlds around red dwarfs might look like, we will sketch possible atmospheres and weather systems. Are we talking thick, humid air and global thunderheads, or a thin, harsh atmosphere with razor-sharp temperature contrasts between day and night? Only then do we let life onto the stage. We will explore speculative ecosystems that could survive under a dim red sun, shadow-loving plants, slow-moving animals clustered near the twilight band, maybe even bioluminescent forests along the Terminator line. It should be noted that this is where we leave the solid ground of measurement and step into carefully constrained imagination. Finally, we bring humans into the picture. Could we build cities in that permanent sunset ring? What would a colony's sky look like? And how would a 19.5-day year reshape culture, calendars, even sleep cycles? Optimistically speaking, Kepler 1649c is one of the most Earth-like habitable candidates we have ever found. But while the orbit and star are well measured, the atmosphere, oceans, and any potential biosphere remain unconfirmed. So it's time to find out the truth, as far as physics allows, and then admit where we are modeling or speculating. Stay with us to the end, because we are going to compare Kepler 1649c with TRAPPIST-1e and Proxima b, and ask a simple question with enormous consequences. If humanity could choose only one of these three as its first true interstellar home, which world would you trust with our future? Red suns and the rules of alien habitability. So if we want to judge Kepler 1649c fairly, we first have to accept a harsh truth. Red suns play by different rules. Red dwarfs are small and dim, so to get Earth-like warmth, a planet has to huddle in close. This means the habitable, or Goldilocks zone, is packed right next to the star, and that changes everything about orbits, climates, and even what a day means. In the hunt for alien life, we often start with the star. How bright is it? How stable? What kind of radiation does it pour onto its planets? A red dwarf, like Kepler 1649, is cool and faint in visible light, but it can be fierce in X-rays and ultraviolet. It should be noted that these high-energy photons and flares can strip atmospheres, boil away oceans, and sterilize surfaces. But while the star sets the stage, it does not write the whole script. On the planetary side, size, mass, atmosphere, and rotation become the counterweight to the star's violence. A slightly larger Earth-like planet can hold on to a thicker atmosphere. That atmosphere can absorb, scatter, or block harmful radiation. This means the same stellar flare that would fry an airless rock might only produce a dramatic aurora on a world with a deep ocean and dense air. Star factors push, planet factors resist, and somewhere in that tug-of-war, surface conditions emerge. Nowhere is this more dramatic than with tidal locking. When a planet orbits very close, gravitational tides slow its spin until one hemisphere always faces the star. One side lives in eternal day, the other in endless night. Imagine standing on the day side under a red sun frozen at one point in the sky, while the night side never sees dawn. Temperature contrasts could be brutal. Scorching desert under the substellar point, deep frozen ice on the far side. But that is only the first order picture. Add a substantial atmosphere or global ocean, and the story shifts. Winds and currents move heat from day to night, smoothing extremes. Climate models of tidally locked worlds show something remarkable: a ring-shaped zone around the Terminator, the line between day and night, where temperatures can settle into Earth-like values. A permanent twilight belt, dim but stable, where liquid water could persist and life might adapt to a sky that is always sunset. Optimistically speaking, this twilight ring may be the prime real estate of the red dwarf universe, and Kepler 1649c sits right at the crossroads of all these principles. Close in orbit, red dwarf host, near Earth insolation, and a likely tendency toward tidal locking. So it's time to find out the truth. Is Kepler 1649c a scorched face and a frozen back, or a world with a narrow, glowing edge where biology could thrive? In the next section, we will step onto that edge and ask what it would actually feel like to stand there. Inside the glow of Kepler 1649, the host star. To understand that twilight edge on Kepler 1649c, we have to step back and look directly into the glow that defines it. What kind of star builds a world of permanent day and endless night in the first place? Kepler 1649 itself is an M-type red dwarf, a small, cool star about 300 light-years away in Cygnus. Compared to our Sun, it is tiny, only a fraction of the Sun's radius, and with far less luminosity. Its surface is cooler, too, so instead of a harsh white-yellow glare, it shines with a deep red-orange glow. This means that even though Kepler 1649c orbits close in, that compact Goldilocks zone is where liquid water could, in principle, exist. Red dwarfs like this are not rare curiosities. They are the rule of the galaxy. It should be noted that roughly 3/4 of the stars in the Milky Way are red dwarfs. Even our nearest stellar neighbor, Proxima Centauri, is one. In the hunt for alien life, that statistic is staggering. If most stars are red dwarfs, then most potentially Earth-like planets in habitable zones probably circle stars like Kepler 1649. There is another twist. While Sun-like stars burn through their fuel in about 10 billion years, red dwarfs sip theirs. Their nuclear fires are so gentle that they can live for trillions of years, hundreds of times longer than the current age of the universe. Optimistically speaking, that gives any habitable planet around them an enormous time window for chemistry to turn into biology, and biology to evolve into something far more complex. If advanced life ever arises there, it could have ages to develop. But while their lifespans are comforting, their neighborhoods are not. Because red dwarfs are so dim, their habitable zones hug the star very tightly. Kepler 1649c whips around its star in just under 20 days, locked into a close orbit where tidal forces are intense. This means the planet is very likely tidally locked with one hemisphere facing the star forever. It also means it sits close to any stellar flares, blasts of high-energy radiation that can strip atmospheres and sterilize surfaces. Here is the pattern interrupt. From far away, Kepler 1649 looks like a gentle ember. Up close, it may behave more like a welding torch. Red dwarfs can unleash powerful ultraviolet and X-ray outbursts, especially when young. For a planet like Kepler 1649c, that radiation could erode an atmosphere over time, unless magnetic fields and dense air fight back. So what would this star look like from the surface? Kepler 1649 would loom larger in the sky than our Sun does from Earth, yet the world beneath would be dimmer, lit by copper and crimson light. The sky might be a perpetual deep twilight near the terminator, and any photosynthetic life would have to tune itself to red and infrared wavelengths, rather than the broad spectrum our plants use. So, let's begin to imagine that landscape. A world bathed in a dull, red noon, carved by tides and radiation, where the star itself dictates every rhythm of climate and potential life. In the next section, we will walk that surface and ask what kinds of oceans, skies, and ecosystems could endure under such a restless red sun. The dark side of red dwarfs, flares, storms, and stripped worlds. But what if that dull red noon hides a far more violent truth? When we talk about red dwarfs as cradles for life, we also have to admit that they can be some of the most dangerous stars in the universe. Red dwarfs are small, cool, and incredibly long-lived. On paper, that sounds perfect for a stable, habitable system. But while their light is gentle, their tempers are not. These stars can unleash stellar flares, sudden eruptions of energy, radiation, and charged particles that dwarf most of what our sun does. A single flare can brighten the star dramatically for minutes to hours, and on many red dwarfs, flares are not rare events. They are part of the daily weather. In the hunt for alien life, that kind of weather matters. Intense ultraviolet and X-ray radiation from repeated flares can slam into a planet's atmosphere, breaking apart molecules like water and carbon dioxide. This means the protective blanket of gas that makes a world feel Earth-like can be shredded into pieces. Once those molecules are broken, the star's stellar wind, a constant stream of high-energy particles, can slowly sweep the fragments away into space over billions of years. Now place a planet close in, right in the Goldilocks zone of a red dwarf. To stay warm enough for liquid water, it must orbit very near its star. But while that keeps the oceans from freezing, it also places the planet in the blast zone. Every major flare becomes a global event. Surfaces can be repeatedly sterilized, organic molecules broken apart faster than they can accumulate. If life arises at all, it may be forced to retreat underground, beneath thick rock, or deep underwater, where the atmosphere and ocean can act as shields. It should be noted that there are possible defenses. A strong magnetic field, like Earth's, can deflect a large fraction of charged particles. A dense, thick atmosphere can absorb harmful radiation higher up, sacrificing its upper layers while keeping the surface relatively protected. Optimistically speaking, some models suggest that tidally locked planets could even shuffle heat and particles around in complex ways, preserving a twilight band that stays temperate and shielded enough for life. But none of these defenses are guaranteed. If a red dwarf is too active, or a planet's magnetic field is weak, atmospheric erosion can win. Over time, the upper atmosphere is stripped away, pressure drops, and oceans may slowly evaporate into space. We are left with a bare, airless surface, a world that once looked promising in the data, now little more than a scorched rock. So it's time to find out the truth. Where does Kepler 1649c fall on this spectrum? Does it hide a powerful magnetic field, thick air, and deep oceans? Or has its red dwarf star already peeled away its atmosphere, leaving only silence? In the next section, we will step closer and ask what the surface itself can tell us. A tiny star, a narrow hope. Why Kepler 1649 still tempts us. And yet, even with that uncertainty hanging over us, Kepler 1649c refuses to be just another cautionary tale about red dwarfs. Why does this particular planet still tempt astronomers to hope, when so many similar worlds look doomed from the start? In the hunt for alien life, most red dwarf planets fall at the extremes. They either hug their star so tightly that their surfaces are blasted, or they drift so far out that any water is locked as ice. Kepler 1649c is different. It sits in a rare sweet spot. It receives about 75% of the light Earth gets from the Sun, and its radius is almost exactly Earth-sized. This means, on paper, it is one of the most Earth-like exoplanets we have ever seen. That on paper matters, because when we talk about the habitable, or Goldilocks zone, there is a big difference between the optimistic outer edges and the conservative middle. Kepler 1649c orbits its small red dwarf in just 19.5 days, but the energy it receives places it right inside that conservative band. Not barely warm enough, not just shy of runaway greenhouse. If it has the right atmosphere, stable, temperate conditions across large regions of the planet are at least physically plausible. It should be noted that this is already better than what we can say for many famous red dwarf systems. TRAPPIST-1, Proxima Centauri, and others have given us incredible data, but they also showcase stars that flare violently, bathing their planets in harsh ultraviolet and X-ray radiation. For Kepler 1649, we do not yet have the same detailed flare statistics. So are we just guessing? Not entirely. Its spectral type and likely age hint that it may be less extreme than the youngest, most volatile red dwarfs. This means that Kepler 1649c might be threading a very narrow needle. A moderately active star, not completely quiet, but not a constant storm. A planet with Earth-like size and gravity, able to hold a dense atmosphere. Add a global magnetic field, and suddenly the picture changes. High-energy particles are deflected, the upper atmosphere is shielded, and surface water, oceans, lakes, or even just scattered seas can survive for billions of years. Optimistically speaking, that combination is exactly what we need if a red sun Earth is ever going to exist. Not too cold and frozen in eternal night, not too scorched and stripped bare. Instead, a world where the day side can host clouds and rain, where the night side can keep a slow, circulating blanket of air, and where the twilight band between them might feel strangely familiar. So let's begin to treat Kepler 1649c as what it truly is, a test case. If any planet around a red dwarf can stay habitable, this may be one of our best bets. And if that hope survives closer scrutiny, it will not just change how we see this one system, it will reshape how we imagine life under red stars across the entire universe. In the next section, we will dive into the surface itself and ask, if you could stand there, what would you actually see and feel? How we found a world in a 19-and-a-half-day year. To imagine standing on Kepler's 1649c, we first have to answer something more basic. How do we even know this planet is there at all? Because we have never seen its surface. We have never seen the planet directly. Instead, we read its presence in the flicker of its star. The Kepler Space Telescope used a deceptively simple trick. If a planet passes in front of its star from our point of view, it blocks a tiny fraction of the starlight. The star appears to dim, just a little, for a few hours. Then, the light returns to normal. It is like watching a miniature eclipse on a graph instead of in the sky. But while that sounds straightforward, the reality is brutal. These dips can be less than 1% of the star's brightness. Stars themselves are noisy. Instruments drift. So let's begin with what Kepler actually did. It stared at the same patch of sky for years, taking brightness measurements every few minutes, building an ocean of data where planets reveal themselves as repeating patterns. In that ocean, Kepler 1649c showed up as a regular heartbeat. Every 19.5 Earth days, the red dwarf Kepler 1649 dimmed by the same tiny amount for the same length of time. This means something small and dark was crossing the star on a precise schedule, locked into a tight orbit far closer than Mercury is to the Sun. The depth of that dip is crucial. A larger planet hides more of the star, causing a deeper eclipse. By comparing how much light was lost to models of the star's size, astronomers inferred that this world is almost exactly the same radius as Earth. It should be noted that the star itself had to be understood first. Its temperature, its radius, its brightness. Only then could they scale the silhouette of the planet. And Kepler 1649c was not the first hint that this system held planets. An inner world, Kepler 1649b, had already been identified. It orbits even closer in, a hotter, more irradiated planet, probably well interior to the Goldilocks zone. When C was confirmed, it completed a picture of a compact two-planet system hugging a faint red dwarf, like beads strung tightly around a dim ember. From the star's brightness and the planet's 19.5-day orbit, scientists could estimate how much energy reaches its top of atmosphere. The answer is striking. About 3/4 of what Earth receives from the Sun. Optimistically speaking, that is right in the range where liquid water could persist on the surface. We still cannot weigh Kepler's 1649c precisely, and we have no direct image of continents, oceans, or clouds. Yet all signs point to a rocky, Earth-like planet in a potentially habitable orbit. In the hunt for alien life, that is enough to make this dim, distant system one of our most compelling targets. And it raises a new question. If we could descend through its atmosphere, what kind of world would actually greet us? So, could anything actually live there? So if we really could drop through those unseen clouds, would we find a second Earth, or something far more alien? At this point, our basic picture of Kepler 1649c sounds almost reassuring. It is a rocky, Earth-sized planet, only about 6% larger than our own world. It orbits in the conservative Goldilocks zone, completing a year in just 19.5 days, and it receives roughly 3/4 of the light Earth gets from the sun. In the hunt for alien life, that combination of size and starlight is about as tempting as it gets. But while those numbers look familiar, the environment that produces them is very different. This planet circles a dim M-type red dwarf, a star far cooler and smaller than the Sun. To get Earth-like energy, Kepler 1649c has to huddle extremely close in its orbit. This means the same side of the planet is almost certainly tidally locked, staring at the star forever, while the opposite hemisphere sits in eternal night. One face in permanent daylight, one in permanent darkness. That is not how Earth works. So, let's begin with the most basic habitability test. Under those conditions, can this world actually keep liquid water on its surface? If the day side is blasted by constant radiation, it could become a baked desert, or even a molten lava landscape. The night side, with no direct starlight at all, might plunge to cryogenic temperatures where any water freezes solid. Without an atmosphere to move heat around, you end up with a scorched hemisphere and a frozen hemisphere, neither truly habitable. It should be noted that we do not yet know whether Kepler 1649c has an atmosphere at all. The Kepler data tell us the planet's size and orbit, but not its air. A thick, Earth-like atmosphere could redistribute heat, creating a more stable climate and perhaps a temperate band around the day-night boundary. But a thin, Mars-like one, or none, would leave the surface exposed to raw stellar radiation. Around an active red dwarf, that is a serious problem for life. And this is where the promising metrics collide with the harsh realities of its star. Red dwarfs flare, emitting bursts of high-energy ultraviolet and X-ray radiation that can strip atmospheres and sterilize surfaces over billions of years. Optimistically speaking, a strong magnetic field or a deep ocean might protect any emerging biosphere. But we also have to ask an uncomfortable question. What if Kepler 1649c is less a twin of Earth and more a scaled-up Mercury, locked close to a restless, dim star? So it's time to find out the truth. In the next sections, we will dive into the orbital mechanics that shape its tides and rotation, explore climate models for tidally locked planets, and even sketch out speculative biospheres that might adapt to eternal day and endless night. Is Kepler 1649c a genuine cradle for life, or a beautiful, cosmic red herring waiting to disappoint us? What we don't know yet. Reading between the light curves. To answer that, we need to admit something up front. How much do we actually know about Kepler 1649c, and how much are we carefully, responsibly imagining? It should be noted that this planet is, for now, mostly a pattern of dips in starlight. From the Kepler spacecraft, we get its radius, about 1.06 times that of Earth, and its orbit, a 19.5-day year, in the conservative Goldilocks zone of a red dwarf star roughly 300 light-years away. That is solid, well-tested data, but beyond that, things get fuzzy very quickly. We do not yet have a direct detection of its atmosphere. No spectrum telling us whether there is nitrogen, carbon dioxide, water vapor, or nothing at all. We do not know the surface composition: rock, ocean, ice, or some exotic mix. We do not even know its exact mass, only estimates based on what typical Earth-like planets of this size tend to weigh. This means every time we mention gravity, pressure, or ocean depth, there is a quiet asterisk hanging over the scene. So where do all those climate scenarios come from? In the hunt for alien life, astronomers have built general models of planets that orbit very close to red dwarf stars and become tidally locked. These simulations show how air and clouds might flow from the scorching day side to the frozen night side, how a terminator ring of permanent sunset could host Earth-like temperatures, or how a thick atmosphere could move heat around and keep oceans liquid. But while those models are powerful, they are not planet-specific measurements. They are blueprints, not photographs. Here is the pattern interrupt. We could be wrong in almost every detail. Kepler 1649c might be an airless rock like Mercury, blasted by stellar flares. It might be a steam-shrouded world, more like a mini Venus than a second Earth. Optimistically speaking, it could also host a calm, dense atmosphere that shields a stable ocean under a soft red sky. Right now, all three possibilities fit the same light curve. And our knowledge is time-bound. The picture we paint today is a snapshot from the early 2020s, limited by what Kepler saw and what our current telescopes can do. Future instruments, perhaps a dedicated exoplanet mission or a next-generation space telescope, could finally tease out the planet's spectrum, weigh it precisely, and even map temperature patterns across its surface. One decisive detection of, say, water vapor or a bare rock emission signal could dramatically revise everything we think we know, for better or worse. So let's begin from a place of honesty. When we talk about skies, oceans, and possible life on this world, we will be explicit about which parts are anchored in physics and which parts are more imaginative extrapolation. Even with all these uncertainties, exploring these scenarios is not just daydreaming. It is how we probe the range of possible lives and landscapes on red sun Earths like Kepler 1649c, and prepare ourselves for the moment when the universe finally shows us one in sharp focus. A planet in the tight embrace of its star. So if Kepler 1649c is one of these red sun Earths, where exactly does it sit in its own miniature cosmos? To understand what life there might endure, we first have to zoom out and look at the whole system. Kepler 1649c races around its red dwarf in just 19.5 Earth days. That is its entire year. By comparison, Mercury takes 88 days to loop once around the Sun. Yet Kepler 1649c is still in the Goldilocks zone of its star, bathing in roughly 3/4 of the light Earth receives. How is that possible when it orbits so close in? The answer lies in the star itself. This star is a small, cool, red dwarf, far dimmer than our Sun. This means the habitable zone is pulled inward, wrapped tightly around the star, like a narrow ring of lukewarm light. Kepler 1649c sits right in that ring. If we could overlay its orbit onto our solar system, you could fit the entire thing well inside Mercury's path, with room to spare. It should be noted that this is not unusual for red dwarf systems. They are compact, efficient, almost clockwork-like. But while the layout is compressed, the planet's energy budget is surprisingly familiar. Because the star's output is so low, Kepler 1649c must huddle close to receive about 75% of Earth's sunlight. This means, on average, the power available to drive climates, oceans, and possibly even an atmosphere is in the same league as our own world. Optimistically speaking, that sets the stage for Earth-like surface temperatures somewhere on the planet. But does that translate into a stable, habitable environment? Kepler 1649c is not alone. In the hunt for alien life, multiple planet systems around red dwarfs are especially interesting. And here we already know of an inner neighbor, Kepler 1649b. It orbits even closer to the star, on a tighter, hotter track. With at least 2 planets packed into such a small volume, their gravity can tug on each other, subtly stretching or squeezing their orbits. Over millions of years, those tiny pulls could change how much starlight Kepler's 1649c receives, nudging its climate between warmer and cooler states. Could that help maintain a dynamic, life-friendly world, or push it toward chaos? We simply do not know yet. So it's time to find out the truth about what this configuration really implies. Kepler's 1649c lives in a precarious balance, close enough to its star for gentle warmth, yet close enough that bursts of radiation could strip or sculpt its atmosphere. It is a planet in a tight embrace, walking a razor's edge between comfort and catastrophe. In the next section, we will dive down from this orbital view and ask a more intimate question. What would a day, if day even exists, feel like on its surface? Locked in daylight, the physics of a 19.5-day year. So, if Kepler 1649c is walking that razor's edge in its orbit, what does that actually feel like under your feet? Because on this world, the idea of a day might be almost meaningless. To understand why, we need to talk about tidal locking. When a planet orbits very close to its star, gravity does more than just keep it in its path. The star's pull stretches the planet slightly, raising tides not in oceans, but in rock. Over millions or billions of years, this constant flexing acts like a brake, slowing the planet's rotation until one hemisphere always faces the star. This is exactly why the moon only shows one face to Earth. So, let's begin to imagine the same effect playing out around a red dwarf. Kepler 1649c orbits its star in just 19.5 Earth days. That is an incredibly tight embrace. It should be noted that at that distance, tidal forces are strong enough that most models predict a fully locked state. This means one side of the planet would be in permanent daylight, the other in eternal night, with the same face always staring back at that dim red sun. What does that do to the geography of light? On the day side, the red dwarf would hang fixed in the sky, never rising, never setting. Just a dull, unblinking crimson disk. Shadows would be permanent. The ground beneath the substellar point, where the star sits straight overhead, could be the warmest, brightest region, perhaps a blazing desert or a steaming ocean eye, depending on the atmosphere. Swing around 180 degrees, and the night side would be locked in darkness, illuminated only by stars and perhaps a faint, ghostly glow from auroras or reflected light from any moons. Between them lies the strangest region of all, the terminator, a narrow twilight band encircling the planet. Here, the star would hover forever on the horizon, casting a perpetual sunset or sunrise glow. In the hunt for alien life, this ring is especially tantalizing. Temperatures here, in many climate simulations of tidally locked worlds, settle into the most Earth-like range, neither scorched nor frozen. If Kepler 1649c is fully locked, its 19.5-day orbit is also the length of its solar day. But while we feel a spinning sky every 24 hours, inhabitants here would experience something else entirely. Weather would be driven not by day-night cycles, but by a constant heat engine. Hot air rising at the substellar point, flowing toward the dark side, cooling, sinking, and sweeping back along the surface. Circadian rhythms might align with slower patterns, perhaps temperature waves, or long-term atmospheric oscillations. Some models allow for partial locking or spin-orbit resonances, like Mercury's 3-2 pattern, where the same side does not always face the star. So it's time to find out the truth about Kepler 1649c in more detail later. But for now, the fully locked scenario is our most likely and simplest guide. So where would you choose to live on such a planet? Under the harsh, unblinking red sun? In the frozen dark beneath a field of stars? Or in the soft, eternal sunset of the twilight ring? And what hidden dangers might each of those regions hold next? Air, oceans, and the twilight ring. Building a climate from scratch. To answer that, we have to ask a brutal question. What does a tidally locked world look like before you give it air and oceans? Without an atmosphere, Kepler 1649c would be a planet of extremes. The day side, staring straight into the red dwarf, would scorch under relentless radiation, heating bare rock to hundreds of degrees. The night side, permanently turned away, would radiate its heat into space and freeze solid. No winds, no clouds, no rain. Just a blasted hemisphere of fire facing a hemisphere of ice, with surface life almost impossible anywhere in between. But add air and everything changes. A thick atmosphere acts like a global conveyor belt, picking up heat on the day side and transporting it toward the night side. Hot air rises near the substellar point, flows outward high in the sky, cools, and sinks on the dark side, then races back along the surface as powerful winds. This means temperature extremes get smoothed out, and the atmosphere itself is less likely to collapse and freeze onto the night side as a permanent cap of ice. So where does that leave us on a world locked to its star? In the hunt for alien life, climate models of similar planets keep pointing to one especially promising region, the Terminator. This is the thin band encircling the planet where day meets night. Here, the star would hover forever on the horizon, painting the sky in a permanent sunset. Temperatures could sit in an almost Earth-like range, cool enough to avoid a runaway greenhouse, warm enough to keep water liquid at the surface. Imagine standing there in the twilight ring, with a dim red sun frozen on the edge of the sky, glowing through towering clouds. On one side, the landscape fades into blinding, overheated day. On the other, it slopes into a deep, star-filled night. It should be noted that even small shifts in atmospheric thickness or composition could move this habitable belt inward or outward, changing which longitudes are safe for life. Now add oceans. Water does not just sit still. It flows, stores heat, and drags climate along with it. On a wet Kepler 1649c, strong ocean currents would carry warmth away from the substellar point, potentially keeping parts of the night side above freezing. Optimistically speaking, you could have open water regions under the dark sky, with slow, ghostly waves lit only by the red glow reflected from the dayside clouds. Here's the twist. Simulations of tidally locked, Earth-sized planets suggest that the brightest, stormiest place might be directly under the star. Massive cloud decks can form above the substellar point, reflecting much of the incoming light and keeping the surface cooler than you'd expect. At the same time, planet-spanning jet streams twist around the globe, feeding colossal storms that march along the twilight ring. So it's time to find out the truth about what those storms, clouds, and currents might mean for real climates, and whether Kepler 1649c is more likely to be an ocean world, a desert, or something far stranger. Under a red noon, what the sky might look like. So if colossal storms prowl the twilight ring, what would it actually feel like to stand there and look up? Because in the hunt for alien life, it is not just temperature and pressure that matter. It is the sky itself. On the day side of Kepler 1649c, noon would never look like noon on Earth. The red dwarf star hangs larger in the sky, a swollen, orange-red disk. Yet the light around you is dimmer, softer, almost like a permanent late afternoon. Shadows stretch longer than you expect, even when the star is high, painted in copper and deep rust instead of sharp black. You could read a book outside, but the pages would never flash white. They would glow a muted cream under that alien sun. But while the star is red, the sky above does not have to be. With a nitrogen-rich atmosphere, Rayleigh scattering still favors shorter wavelengths. This means the vault overhead could be a subdued blue, even leaning toward violet, because the star still emits some blue and ultraviolet light. It should be noted that this scattered light is filtered through a red-weighted spectrum, so the result is strange to our eyes. A bluish-purple dome that fades toward wine-colored and magenta tones near the horizon, especially where dust or water vapor thickens the air. Now move toward the terminator, the Goldilocks zone of light itself. Here, the star never climbs far above the horizon. It just hovers, a permanent, swollen ember caught in eternal sunset. Landscapes in this twilight ring are bathed in endless, golden red light, like the last 5 minutes of a clear Earth evening stretched across an entire world. Clouds tower high, their tops glowing pink, their undersides bruised purple. Jet streams feed them from the blazing day side and the freezing night side. So storms here are frequent, dramatic, and slow-moving, flashing with lightning that turns the red clouds white for an instant. Cross into the night side, and the star finally slips below the horizon, but not completely. A faint red band still glows along the edge of the world, scattered through the upper atmosphere. Above, the sky explodes with stars. With so little scattered daylight, the Milky Way would be a bright, textured river. And when the red dwarf flares, charged particles rush along magnetic field lines, igniting auroras that ripple across the dark hemisphere in curtains of crimson, green, and violet. Imagine an entire continent lit only by starlight and slow, silent waves of color.
So what does this mean for life?
Eyes here might evolve to be extraordinarily sensitive, tuned to reds and near-infrared, perhaps seeing contrast and copper shadows the way we see color on a sunny beach. Sleep cycles could follow subtle changes in cloud brightness rather than a rising and setting star. Art and architecture, if an intelligent civilization exists, might celebrate silhouettes and glow. Buildings designed to catch the low horizontal light, pigments chosen to blaze under red suns and auroral skies. And as we will see next, these same conditions could dictate where oceans, ice, and forests are even able to exist on this planet at all. Radiation, shields, and survival. Can life endure the storms? But under those auroral skies, there's a harsher truth we have to face. Kepler's 1649c does not just orbit a gentle red lantern in space. It circles an active red dwarf star, and that means radiation. Intense ultraviolet light, bursts of X-rays, and swarms of energetic particles can erupt during stellar flares. In the hunt for alien life, this is one of the biggest double-edged swords. The same compact star that keeps the planet in the Goldilocks zone can also threaten to strip its atmosphere and shred delicate molecules like DNA. So what would that look like on the surface? During a major flare, the sky above the dayside could brighten in hard, bluish light, followed by a storm of charged particles slamming into the planet. Without protection, those particles can erode the upper atmosphere over millions of years, driving off lighter gases and breaking apart water vapor. This means the long-term habitability of Kepler 1649c is tightly linked to its defenses. The first line of defense is invisible, a magnetic field. If this Earth-like planet has a molten, churning core, it could generate a magnetosphere that wraps the world in a protective bubble, deflecting many charged particles away. Earth's own field funnels particles into the poles, creating auroras instead of global sterilization. It should be noted that if Kepler 1649c is tidally locked, keeping one face to its star, the way its interior cools and stirs might be very different. So whether that magnetic shield exists is still an open question.
Next comes the atmosphere itself.
A dense blanket of gas can soak up high-energy photons before they reach the ground. Ozone on Earth does this with ultraviolet. On Kepler's 1649c, other oxygen or sulfur-bearing molecules could play a similar role, sculpted over time by the star's radiation. Optimistically speaking, a thick, stable atmosphere could turn deadly flares into spectacular light shows while leaving the surface comparatively calm. And even if the surface is harsh, life does not have to stay there. Oceans are superb radiation shields. Just a few meters of water can block most UV and X-rays. Ice caps, deep lakes, and even layers of soil or porous rock can protect microbial communities beneath. Forest-like canopies, if they exist, might act as living umbrellas, with upper layers sacrificing themselves to the radiation while shaded ecosystems thrive below. But what if life adapts instead of hiding? Some Earth microbes repair DNA at astonishing speeds, or produce dark pigments that act like microscopic sunscreen. Others use radiation indirectly as an energy source, harvesting chemical gradients created by high-energy particles. So let's begin to imagine organisms on Kepler's 1649c with ultra-robust genomes, reflective shells, or crimson pigments tuned to their star's violent spectrum. So it's time to find out the truth. If life exists on Kepler's 1649c, is it clinging to the twilight shores of a stormy ocean, or thriving in deep, radiation-sheltered biospheres we can barely imagine, waiting for us in the dark? Alien forests under a crimson sun. If life is hiding in that darkness, what kind of forest would it build under a crimson sun? On Earth, we take green for granted, but under a red dwarf, like Kepler's 1649, even the basic rules of color could be rewritten. We know that on our own planet, plants use chlorophyll tuned to the sun's spectrum, grabbing mostly red and blue light and reflecting green. This means their entire energy budget is based on a yellow-white star. But Kepler's 1649 is cooler, redder, and pours out much more of its power in deep red and infrared. So let's begin with a simple question. If you were a photosynthetic organism here, why waste photons your star barely provides? In the hunt for alien life, that pushes us toward very different pigments. Instead of chlorophyll as we know it, life on Kepler's 1649c might evolve molecules that soak up red and infrared with ruthless efficiency. It should be noted that on Earth, some bacteria already use bacteriochlorophyll to harvest near-infrared in dim ponds. Scale that idea up to a whole biosphere, and the result is striking. Forests might not be bright, leafy canopies at all, but vast, shadowy carpets of almost black foliage. Leaves could be deep purples or wine reds, tuned to the star's spectrum, or even show metallic sheens that scatter deadly flare radiation while trapping precious heat. Imagine walking across the twilight ring of this planet, looking out over fields so dark they seem like spilled ink, only catching a dull crimson glint when the low star skims the horizon. That twilight ring is key. On a tidally locked world, the band between day and night could be the most stable, truly Goldilocks zone at the surface. Constant, low-angle light, relatively gentle winds, and moderate temperatures might allow dense, layered ecosystems. Moss-like mats hugging the ground, vine analogs climbing toward the ruddy glow, and fungal webs recycling every last scrap of organic matter. Meanwhile, the permanent day side could be harsher, hosting hardier, flare-resistant life with reflective coatings or buried stems that only expose small photosynthetic patches during quieter moments of the star. But what feeds on what in such an alien system? Deep oceans, shielded from radiation, might host chemosynthetic microbes using chemical gradients from the interior, rather than starlight at all. Above them, filter feeders could drift in perpetual dusk seas, straining out crimson-tinted plankton. At the surface, slow, broad-mouthed grazers might shuffle through those dark forests, followed by predators using heat-sensitive organs to track warm bodies under the dim red sky. All of this would be shaped by the planet's slow day, intense radiation cycles, and potentially extreme weather. Long, flare-driven energy pulses could act like super seasons, triggering synchronized blooms and migrations. Optimistically speaking, that could make life on Kepler 1649c both fragile and incredibly resilient, always one storm away from disaster, yet always adapting.
So it's time to find out the truth.
If such forests exist, could we ever see their colors from light years away? Or will the next section show that their signatures are already hiding in the data? Cities in eternal sunset, if intelligence evolved there. If forests really do bloom beneath that red sky, what kind of minds might be walking between them? On a planet where a day and a year both last 19.5 Earth days, how would an intelligent species even think about time? On Kepler 1649c, the familiar rhythm of sunrise and sunset barely exists. The planet almost certainly keeps the same face toward its red dwarf star, so the cycle that matters is not spinning from night to day, but drifting through patterns of flares, winds, and long, slow weather pulses. This means their calendars might be written in storms. A week could be the interval between major stellar outbursts. A month, the time it takes the atmosphere to cool and reorganize. Instead of saying, "see you tomorrow," they might say, "see you after the next quieting," referring to the calm that follows a flare season. In the hunt for alien life, that is a profound shift. Time anchored not to geometry, but to the moods of a star. Biology would follow the same logic. Under a dim red sun, eyes that waste photons would be a disadvantage. So let's begin with vision. We can imagine large, forward-facing eyes, glossy and faceted, tuned to red and infrared, able to read heat as easily as we read color. Transparent eyelids or multiple membranes could snap shut when a flare lights up the sky, protecting delicate retinas from sudden radiation. Skin, if they have it, would not look fragile. It should be noted that red dwarf stars can blast their planets with high-energy particles. To survive, these beings might wear their armor from birth. Thick, layered hides, reflective scales, or even a chitin-like exoskeleton laced with pigments that absorb and repair radiation damage. Perhaps their children shed protective plates as they grow, each layer recording a history of storms like tree rings.
Where would such a civilization build its cities? Not under the blazing substellar point, and not in the frozen dark. The Goldilocks zone on the surface is the twilight ring, the permanent terminator, where the star forever hovers near the horizon. Here they could balance steady energy from the day side with cool, dense air spilling from the night side, driving constant winds that their engineers might learn to tame. Picture cities hugging this ring, stretched out like necklaces around the planet. Tall towers rise into the copper sky, their tops crowned with vast mirrors. These mirrors redirect just enough light deeper into the twilight, feeding farms and algae pools without overheating them. On the night side slopes, insulated conduits carry warmth outward, while cold air is channeled back toward the light, a global breathing system powered by the difference between everlasting day and everlasting night. Under such a sky, how would they tell stories about their star? A red dwarf that flares, darkens, and flares again is both a gentle hearth and a threat. Mythology might describe it as a temperamental deity, a life-giver whose anger arrives as white-hot scars across the heavens. Priests and scientists could be the same class of people, carefully tracking flare cycles, building early warning systems, and turning prophecy into prediction. So it's time to find out the truth. Would such a culture see calm periods as sacred holidays, moments when the star rests and the atmosphere clears? Optimistically speaking, their science might begin as an attempt to appease the sky and end as a physics of stellar weather more advanced than our own.
Now imagine the ultimate reversal. One night, if we can call it that, an observatory on the Terminator detects a faint yellow-white star in the distance. Careful measurements reveal a small blue dot in orbit, our Sun, our Earth. What would they think of us? To eyes evolved under a dim red sun, the sun would look harsh, almost violent, pouring out several times more visible light than their star. Earth might appear as a dangerously bright anomaly, its blue oceans reflecting a glare they find almost painful. Would they see it as a world where life is constantly threatened by excess energy, a place of short, frantic days and blinding skies?
Or would it look like a miracle? From Kepler 1649c, a temperate blue planet orbiting a stable yellow star might be the ultimate dream. No flares strong enough to strip an atmosphere, a sky rich in photons, and a wide, habitable band that wraps all the way around the globe. In their legends, the ideal world could be one where the star rises and sets, where time is gentle, and where forests do not have to brace for radiation storms. In the hunt for alien life, that perspective matters, because while we imagine their world as harsh and marginal, they might look back and see ours as the true paradise. And in the next section, we will turn the telescope around again and ask a final question. If both civilizations reached for the same signal at the same time, would the physics of their stars let them ever hear each other at all? Kepler 1649c versus TRAPPIST-1e versus Proxima b. So if a Kepler 1649c civilization is listening, where does their world sit among our other great red dwarf candidates for life? In the hunt for alien life, we now have a small, elite club of planets, and each one comes with very different fine print. So let's begin with the celebrity, TRAPPIST-1e. This planet orbits an ultra-cool red dwarf about 40 light-years away, in a system of 7 tightly packed, Earth-sized worlds. TRAPPIST-1e is roughly Earth-sized, tidally locked, and sits near the middle of its star's Goldilocks zone, receiving around 2/3 of the light Earth gets from the Sun. A year there lasts only about 6 Earth days, but while the star is relatively calm for a red dwarf, it still flares, and all those planets sit extremely close in, bathing their atmospheres in high-energy radiation. Proxima b, by contrast, is the terrifying neighbor. It orbits Proxima Centauri, the closest star to the Sun, just over 4 light-years away. This planet is roughly Earth mass, in the habitable zone, with an orbital period of about 11 days and insolation similar to Earth's. On paper, that sounds ideal. But Proxima is a notoriously active red dwarf, with violent flares and intense X-ray and ultraviolet bursts. This means any atmosphere on Proxima b has been fighting for its life for billions of years. Where does Kepler 1649c fit between these two extremes? It should be noted that Kepler 1649c orbits a small M-type red dwarf about 300 light-years away, with a year of roughly 19.5 days. The planet is about 1.06 times Earth's radius and receives roughly 75% of the starlight Earth gets. That places it close to the center of the conservative habitable zone, with insolation more Earth-like than TRAPPIST-1e and at least comparable to Proxima b. Stellar activity is where the trade-offs become interesting. The TRAPPIST-1 star is relatively quiet for its class, yet its planets sit so close that even modest flares matter. Proxima Centauri is dramatically more violent, with super flares that could strip or sterilize atmospheres outright. Kepler 1649's red dwarf appears less extreme than Proxima, and because Kepler 1649c orbits a bit farther out in relative terms, its upper atmosphere might experience a slightly kinder radiation environment. Optimistically speaking, that combination of near-Earth size, near-Earth insolation, and a not-quite-so-insane host star makes Kepler 1649c one of the most compelling Earth-like planets we have around a red dwarf. TRAPPIST-1e offers a compact system and a quieter star, Proxima b offers proximity, and Kepler's 1649c offers balance. So it's time to find out the truth. If we could place the same ocean, the same atmosphere on all three, which world would actually treat that fragile film of life the best, and which one would betray it first when the star decides to erupt? If we went there, first boots on a red sun shore. So if these three worlds are our test beds, we have to ask a harder question. What would it actually feel like to stand on one of them? Not in a simulation, not in a climate model, with our own boots on alien ground. So, let's begin with a future where we have solved the problem of crossing interstellar space. After centuries in a generational ship or a slow armada of fusion sails, humanity finally slips into orbit around Kepler 1649c. Below us is a planet almost Earth-sized, locked to its red dwarf star, one hemisphere frozen in endless night, the other facing a permanent, glowing dawn. The mission planners choose the only place that looks truly habitable, the twilight ring along the terminator, where temperatures balance between scorching and frozen. Descent starts over that dim, copper-lit band. As the lander drops, the planet's atmosphere thickens around us. Is it clear and blue, or hazy and rust-colored from photochemistry driven by the star's flares? We do not know yet, but imagine a sky stained red, the light filtered as if through perpetual sunset. To one side, the substellar region boils with towering storm systems. Lightning flickers inside anvils that climb 3 times higher than Earth's thunderheads, visible even from orbit. But while the day side looks violent, the terminator itself might be strangely calm. The lander punches through the last cloud layer, buffeted by crosswinds as hot air from the day side collides with cold night air. Instruments scream about pressure gradients, trace gases, radiation levels. This means every meter of descent is an experiment in habitability. Then comes the moment that, in the hunt for alien life, we have dreamed about for generations. The hatch opens. Gravity pulls a little less than on Earth, but not by much. Each step feels just slightly too light, almost like walking after you take off a heavy backpack. The light is cooler and dimmer, a copper wash that makes colors look subtly wrong. The red dwarf star hangs low over the horizon, huge compared to our sun, and almost motionless. A day here is not a spin of the planet, but a slow precession in orbit. The star will creep, not rise. You look up. The constellations are unfamiliar, the Milky Way tilted at a new angle. It should be noted that this sky, for all its beauty, is not entirely friendly. Radiation monitors tick upward when the star flares. The atmosphere may shield most of it, or not. Immediate hazards crowd the checklist. Unknown microbes in the soil and air, demanding sealed suits and sterilization protocols. Sudden radiation spikes during stellar outbursts, forcing colonists into buried shelters. Extreme weather as heat is pumped from the substellar point toward the dark hemisphere, driving jet streams that never sleep. And beneath it all, a psychological challenge, building farms, cities, and power grids in a world with no natural day-night cycle, where morning is whatever the clock says it is. Pattern interrupt. Imagine power failing. The star flares. The sky brightens blood red. Instruments overload. Is this a habitable shore or a warning sign etched in light? Optimistically speaking, Kepler 1649c could host oceans, clouds, maybe even native life beneath that strange glow. But standing there, suit visor reflecting a frozen red sun, would it feel like arriving on a new Earth? Or like cautiously exploring a beautiful but hostile alien museum exhibit? Terraforming a twilight world. So if our first steps on Kepler 1649c feel like walking through a museum, the next question is uncomfortable. Do we leave the exhibits untouched, or start rearranging the entire gallery? Terraforming is, at its core, an act of planetary editing. We take a hostile world and try to rewrite its atmosphere, temperature, and surface water until it becomes something more Earth-like. On a fast-spinning planet, we spread warmth and moisture around the globe.
But while that basic idea sounds simple, a tidally locked world breaks our usual playbook. How do you reshape a planet where noon never moves, and the Goldilocks zone is a thin circle of eternal sunset? So let's begin with the atmosphere. If Kepler 1649c has only a thin envelope of gas, we might try to thicken it with greenhouse molecules like CO2 or engineered analogs, trapping more of the red dwarf's dim light and pushing warmth from the day side toward the night. If it is already smothered in dense air, we might instead strip or chemically bind greenhouse gases, letting heat escape to space. This means climate control becomes a balancing act. Too much blanket and we risk a runaway greenhouse. Too little and the night side could freeze into a permanent expanding glacier. Engineers would not be limited to the surface. Imagine vast orbital mirrors locked into the same 19.5-day orbit, redirecting starlight onto the frozen hemisphere, carving out islands of twilight where only darkness existed before. Or, conversely, gigantic shades dimming the blazing substellar point, preventing oceans from boiling away. It should be noted that on a world like this, even a few % change in illumination could shift the entire pattern of winds, clouds, and habitability.
Then there is biology. In the hunt for alien life, we usually think about discovering microbes, not deploying them. Yet one terraforming strategy would be to seed the Terminator zone with hardy, engineered organisms, extremophile microbes that feed on the local rock, exhale oxygen or other useful gases, and slowly paint the planet with soil. Over centuries, they could build up an atmosphere more comfortable for us, turning bare rock into a living filter. But what if we are not first? If Kepler 1649c already hosts native ecosystems, perhaps dark, lichen-like mats clinging to the red-lit dayside, or chemotrophic colonies thriving in subglacial oceans on the night side, do we have the right to overwrite them? A biosphere tuned to a red star and permanent twilight might be fragile in ways we do not yet understand. So it's time to find out the truth. Are we gardeners, guests, or invaders? Even if we chose to reshape the planet, the engineering challenges would be immense. Any attempt to redistribute heat risks tipping the climate into global glaciation or a moist greenhouse that sterilizes the surface. Building infrastructure across such extreme regional differences, towering solar farms under the red sun, fusion-powered outposts in the dark, transport corridors straddling hurricane-force winds at the boundary, would stretch our technology to its limits. Which leaves us with a deeper dilemma. Do we bend Kepler 1649c toward Earth norms, flattening its strangeness? Or do we adapt ourselves through habitats, bioengineering, and culture to live within its alien but stable twilight ring? Optimistically speaking, the future of this planet might not be about conquering it at all, but learning how to share a sky where the sun never rises or sets. And if we choose adaptation over domination, what would a truly twilight civilization look like? That is where we turn next. How we'll actually study this world from afar. So if we dream of a twilight civilization on Kepler 1649c, how do we actually test any of this from 300 light-years away? How do we move from poetic climate maps in our heads to hard numbers written in starlight? In the hunt for alien life, our sharpest tool right now is transmission spectroscopy. When Kepler 1649c crosses in front of its red dwarf star, a tiny fraction of the starlight filters through whatever atmosphere the planet may have. Different gases absorb different colors of light, leaving spectral fingerprints. Water vapor, carbon dioxide, even oxygen, each carve out their own distinctive notches. By comparing the star's spectrum during a transit to its spectrum when the planet is out of the way, we can, in principle, read the chemical recipe of that alien sky. This sounds straightforward, but while the method is elegant, the execution is brutal. Kepler 1649 is a relatively faint, small red dwarf. The planet is only slightly larger than Earth. This means the atmospheric signal is incredibly thin, buried in noise.
Even with powerful telescopes, we need many repeated transits and exquisite stability to pick out a few parts per million change in the star's light. It should be noted that, unlike the TRAPPIST-1 system, we do not yet have James Webb Space Telescope quality data for this specific planet. So let's begin with what we can realistically expect. JWST might struggle to get a clean spectrum here, simply because the star is dimmer and more distant than its famous cousins. The current generation of space telescopes can tell us the planet's size, its orbit, and that it sits in the conservative Goldilocks zone, receiving about 3/4 of the light Earth gets from the sun. But to probe clouds, greenhouse gases, or potential biosignatures, we will likely need the next wave of instruments. On the ground, extremely large telescopes, such as the ELT and the 30-meter telescope, will use vast mirrors and advanced adaptive optics to squeeze every photon out of this system. Above the atmosphere, proposed missions like the Habitable Worlds Observatory and LUVOIR-class concepts aim to combine huge mirrors with ultra-stable spectrographs. Optimistically speaking, these observatories could finally dissect Kepler 1649c's atmosphere, turning a faint dip in brightness into a detailed climate report. Transmission is only half the story. By watching how the total light from the system changes as the planet orbits, we can build phase curves, faint variations as different hemispheres rotate in and out of view. This means we can infer how heat flows from the permanent day side to the night side, whether the terminator hosts thick clouds, even whether the planet's surface is dominated by rock, ocean, or ice. Each new piece of data will either support or tear apart our speculative picture. Slowly, theory will give way to measurement, and Kepler 1649c will shift from a canvas of maybes into a characterized world. But when we finally see its true face, will it look more like a second Earth or something far stranger than we are prepared for? A day in the life on Kepler 1649c. So if theory will soon give way to measurement, what would it actually feel like to live there? Imagine we drop in on one ordinary day on Kepler 1649c. Our colonist wakes in the twilight ring, the narrow belt where day never quite arrives and night never fully wins. Outside the habitat window, the red dwarf star hangs at the same low angle it always does, a copper coin frozen above the horizon. It should be noted that on a tidally locked planet, the sky does not tell you the time. Clocks do. Shift alarms replace sunrises. Stepping into the main corridor, the first thing they pass is the light management panel. The habitat's white LEDs slowly dim toward a warmer hue, mimicking an Earth-like morning that the planet itself never provides. This means circadian rhythms are an engineering project, not a gift from the sky. Without these systems, sleep, mood, and health would drift as strangely as the local orbit. Outside, the settlement sprawls under a copper-tinged glow. Shadows are long and permanent, stretching away from the red sun in sharp, repeating lines. The air, thinned to Earth-like pressure by careful terraforming, or domes, is cool, more like a high-altitude valley than the tropics. In the hunt for alien life, we often imagine steamy jungles, but here, the Goldilocks zone feels crisp, almost autumnal. Work detail today is on the outer farms. The crops are not familiar green. Leaves are darker, almost black-violet, tuned by genetic engineering to drink every photon from the red spectrum. Rows of these plants march toward the brighter day side, shielded by smart canopies that tilt and polarize, trimming flare light while letting in steady illumination. Is this still agriculture as we know it, or something new? Halfway between botany and astrophysics. Halfway through the shift, a chime cuts through the hum of machinery. Pattern interrupt. Everyone stops. The radiation forecast is updated. A moderate flare is building on the far side of the star, and models suggest a glancing blow in a few hours. So, let's begin the practice dance. Exterior work is reprioritized,
sensitive instruments are safed, and children in the education dome rehearse, once again, the calm walk to underground shelters. From a ridge above the settlement, our colonist watches the planet breathe. To one side, low clouds slide in from the blazing dayside, their tops lit a dull orange, carrying heat and moisture toward the twilight ring. To the other, the sky deepens toward the night side, where stars are always faintly visible opposite the red sun, as if the universe itself is on permanent display. But while Earth's weather marches west with a spinning globe, here the fronts creep in from a fixed direction, like slow tides of air. Later, under the habitat's dimmed evening lights, people share data and stories. Did the new algae strain handle the cooler temperatures? How did the flare models compare to reality? Optimistically speaking, each quiet, artificial sunset makes the settlement a little more self-sufficient, a little more at home. So it's time to find out the truth. Would we ever feel fully adapted to a world where the sky barely changes, yet everything else never stops? In the next section, we will step back from this single day and ask what long-term cultures, ecologies, and even civilizations might become on a planet like Kepler 1649c.
Would you volunteer for a one-way ticket?
So if this really were our new sky, the question becomes unavoidable. Would you volunteer for a one-way ticket to Kepler 1649c? Because that is what we are really talking about here. Not just a clever simulation, but a permanent move. No return launch window, no quick hop back to Earth if the constant twilight starts to feel a little too alien. On paper, the trade-offs look almost reasonable. Gravity close to Earth's, so your bones and muscles stay strong. Starlight at about 75% of what we receive from the sun, placing this planet right in a conservative Goldilocks zone. Optimistically speaking, that makes it one of the most Earth-like targets in the hunt for alien life anywhere in our part of the galaxy. But while the numbers look comforting, the lived experience would be very different. You would leave behind blue skies and white clouds and step into a world lit by a dim red dwarf, where the sky is copper and violet, and the brightest light never climbs much higher than a permanent late afternoon. There is no familiar 24-hour rhythm. Instead, the Terminator ring offers endless sunset. The day side crawls through a slow-motion day over weeks, and the night side never sees dawn at all. Could you say goodbye to the constellations you grew up with? Orion, the Big Dipper, the Southern Cross, all gone. Replaced by an unfamiliar star pattern and a host star so faint you might almost stare straight at it. This means your sense of direction, even your sense of time, would have to be rebuilt from scratch. Psychologically, that matters. In the twilight band, you would never see a true noon or a true midnight. Just a dim glow on the horizon that barely shifts, and perhaps a darker arc behind you where the atmosphere fades into permanent night. Circadian rhythms, already fragile on space stations, would be under constant assault. How long before day and night become purely artificial words on a colony clock?
And beyond the sky, there is the isolation. A small outpost, hundreds of light years from the solar system, with radio messages taking centuries. It should be noted that this is not like Mars, where a delayed conversation is still a conversation. Here, you speak once to Earth, and no one alive, when you answer, will ever hear the reply. So why go? Because the allure is enormous. To stand on an Earth-sized planet that almost slipped through the noise of Kepler's data, to help decide whether its atmosphere shelters oceans, continents, maybe even a native biosphere clinging to that temperate ring. So, let's begin to be honest. Part of us wants to be there first, to write the opening chapter of a new human civilization. In the hunt for alien life, this is the frontier. You might be the first to sample an alien ocean, to map forests under a red sun, or to confirm that the planet is utterly barren, and then choose how to seed it with Earth life. So it's time to find out the truth for yourself. As we move into the final sections, we will compare Kepler 1649c with other candidate worlds. Start forming your answer now. If you had to choose humanity's next home, would you step onto this red-lit shore and never look back? What Kepler 1649c really teaches us about Earth-like. We have called Kepler 1649c one of the most Earth-like planets we know. But after everything we have seen, what does that label really mean? So let's begin with the numbers, because they are seductive. Kepler 1649c is almost exactly our size, about 1.06 times Earth's radius, with a similar surface gravity. It receives roughly 3/4 of the light Earth gets from the Sun, placing it neatly in the Goldilocks zone of its red dwarf star. It orbits once every 19.5 days, almost certainly tidally locked, and we still do not know if it holds a thick atmosphere, a thin one, or none at all under the assault of stellar radiation. On paper, this looks like home. But while the spreadsheet says Earth-like, the reality could be profoundly alien. A planet with our gravity and broadly similar temperatures might still divide its surface into eternal day and endless night. The sky could glow a deep red instead of blue. The star above might flare with bursts of X-rays and ultraviolet light, powerful enough to strip gases from the atmosphere and sterilize exposed ground.
This means that similar numbers can hide very different worlds. Two planets can share radius, insolation, and even average temperature, yet one hosts continents, oceans, and forests, while the other offers a single habitable twilight ring clinging to a narrow band between scorching noon and frozen midnight. It should be noted that our current data on Kepler 1649c cannot yet tell these scenarios apart. We are still guessing at winds, clouds, oceans, and magnetic fields. In the hunt for alien life, Earth-like has become a kind of shorthand, a promise that a planet might be comfortable, safe, and welcoming. But Kepler 1649c reminds us that it is only a first filter. The real questions begin afterwards. What is the atmosphere made of? How stable is the climate over billions of years? How often does the star erupt? And how deeply does that radiation penetrate? Without answers, surface habitability remains an open and very fragile possibility. There is also a larger cosmic lesson here. Most habitable zone planets in the galaxy probably orbit red dwarfs. Optimistically speaking, if life is common, then most living things in the universe may look up at dim red suns, not bright yellow ones like ours. Their skies, rhythms of day and night, and evolutionary pressures would be tuned to a very different kind of system. So it's time to find out the truth about our own expectations. Given everything we have explored, is Kepler 1649c truly a place to call home, or a harsh laboratory we study from afar? In the next section, we will weigh it directly against other candidate worlds and ask whether our blue, temperate Earth is not just habitable, but uniquely precious. Choose your red sun future. So if we had to choose right now where humanity plants its first flag around another star, which world wins? Would it be Kepler 1649c under its deep red sun, TRAPPIST 1e in that tightly packed clockwork system, or Proxima b circling our nearest stellar neighbor? In the hunt for alien life, those three names come up again and again. But while they all sit in some version of a Goldilocks zone, the trade-offs are very different. Kepler 1649c offers Earth-like starlight
but orbits a distant red dwarf about 300 light-years away. TRAPPIST-1e lives in a 7-planet system where worlds crowd the sky. Proxima b is practically on our cosmic doorstep, yet bathed in violent flares. So which planet would you actually bet our future on?
This means we want you to act as mission planners for the entire human species. In the comments, pick your colony world and explain your reasoning. Do you prioritize distance and choose Proxima b simply because it is closest, even if its star may strip away an atmosphere? Do you favor climate stability and potential Earth-like conditions on TRAPPIST-1e, accepting a sky dominated by a dim red star and neighboring planets looming overhead? Or do you side with Kepler 1649c, with its more gentle insolation and potentially calmer atmosphere, even though it lies far across the galaxy? It should be noted that there is no single correct answer here, only different visions of our future. Think about radiation levels from each red dwarf, the likelihood of a protective atmosphere surviving, the challenge of a tidally locked climate with one face frozen and one baked, and the sheer beauty or strangeness of each sky. Would you rather stand in TRAPPIST-1e's twilight, watching other planets rise as bright disks, or on Kepler 1649c's Terminator line, where the red sun hangs forever on the horizon? To turn this into more than a thought experiment, we have set up a poll comparing these exoplanets. So let's begin treating this like a real decision. Click your choice there, then justify it below. Optimistically speaking, the way you weigh these worlds reflects how we, as a civilization, balance risk, comfort, and curiosity in the wider universe. Now a more personal question. Would you volunteer for a one-way mission to Kepler 1649c? If a starship were ready, no return ticket, would you step on board? Tell us your biggest fear. Is it the long, dark voyage, the unknown atmosphere, the possibility that the planet is lifeless and silent? And what is your greatest hope? Building the first city under a red sun? Or maybe watching alien clouds drift over an ocean that has never known Earth? Every comment and question feeds back into our own journey. This means you are helping shape which worlds we explore next, both in future videos and one day with real starships. Because the real mystery is not only which planet is most habitable, but which future we will dare to choose. And in the next section, we will push that choice to its extreme. The red sun in our future night sky, both in future videos and one day with real starships. Because the real mystery is not only which planet is most habitable, but which future we will dare to choose. And in the next section, we will push that choice to its extreme. So let's begin with a final image. Picture a night on Kepler 1649c, billions of years from now. The sky is darker than Earth's, the Milky Way a dense, braided river of light. Above a rocky plain, our red dwarf star hangs low, not blazing white like the sun, but a deep ember casting long crimson shadows across ice, rock, and perhaps the lights of a distant city. On a ridge, a small group of humans stands in thin, carefully engineered air. Their bodies and technology are adapted to this world, to this red sun, to a year that lasts just 19.5 of our old days. They are not visitors anymore. This planet is home. One of them raises a hand, pointing at a pinprick of brightness almost lost in the crowded sky. It should be noted that from 300 light-years away, our sun would be nothing more than a faint star, one anonymous point in the vast system of the Milky Way. Yet for them, that point is an entire origin story. Oceans, forests, cities, every ancestor they have ever traced. Do they feel homesick for a world most of them have never seen? Or does home now mean something larger? Any habitable shore where life can stand, breathe,
and look up at a sky full of possibilities. In the hunt for alien life, worlds like Kepler 1649c force us to expand our definition of what is truly Earth-like. This means home is no longer a single blue planet in a narrow Goldilocks zone, but a spectrum of climates and colors under very different stars. A red dwarf sun, a 19.5-day orbit, a twilight band where day and night meet in permanent glowing dusk. Today, all we have are light curves, orbital periods, and carefully filtered data. But every time we imagine seas under that red sky, or an atmosphere thick enough to cradle life, we are taking the first real step from data point to destination. Optimistically speaking, the journey to Kepler 1649c begins not with rockets, but with questions. So it's time to find out the truth about how far that curiosity can carry us. If you want to keep building this mental map of future homes, one exoplanet, one star, one possible sky at a time, make sure you subscribe and stay with us as we explore the next world in this vast universe. And tonight, when you look up at the stars, remember, somewhere out there, Kepler 1649c is circling its red sun. One day, under that dim crimson light, someone might be looking back, wondering which distant point of light, far across the dark, was once your entire world.